Good morning, everyone. If I may ask the folks who are standing if you want to come closer and sit, we're going to start. How is everybody doing? Good? All survived immigration and getting into Brussels well? First of all, I'm ETHCC. For those of you who don't know me, I'm the CEO of Fhenix, and we're an ETH-based L2 and coprocessor that uses FHE to bring confidentiality to Ethereum. I want to welcome you all for coming for Encryption Day. This is the second Encryption Day that we're running. The first one was in Denver, and we're super excited to see so many people here, especially given the fact that there are so many other events to attend. For me, this is a really strong sentiment of where encryption is needed in the blockchain ecosystem and where we're heading to. We've created an amazing set of presenters and speakers for today. We're going to talk about zero-knowledge proofs, MPC, TEs, and FHEs. We wanted to make sure that the discussions will not just cover the technologies, but also use cases that are going to shape this industry in the next couple of years. We have the likes of Tarun Chitra, Justin Drake, Guy Ziskin, Pascal Pallier, Eli Ben-Sisson, and many others that are going to talk in the next couple of hours. You can actually see the full agenda on the website. Before we start, I just want to make sure to thank our sponsors, Fairblock and Lambda Class. Both founders are either here or going to be here. Make sure you find them and hear more about the projects that they're leading. And lastly, I also want to thank my one-in-a-million amazing team for the work that they've done in setting up this event. So thank you all. For those of you who want to learn more about Fhenix, look up Kyle. He's going to be here in a minute for the development-related questions, and Shinju for partnership and growth. And with that, I want to invite Guy Ziskin to give the first talk on FHE rollups and coprocessors. Thank you.
Okay, hey everyone. Thanks for coming this morning. You know, this was a very hard talk to set up because I wasn't sure what's the right level to put it at. So for some of you, this may be too basic. For some of you, this might be, you know, just like hit the spot. So if it's too basic, good for you. I'll be here the entire day. You know, feel free to talk to me. I'm happy to give more details. We have 20 minutes. I really can't cover everything, but there's many more details that can go into those slides. But you know, if you like to geek out and nerd out about them, then I'm happy to. So, you know, if you're here, you know blockchains. I really don't need to kind of give you an introduction. There's many kinds of blockchains. They can be for payments, for smart contracts, maybe even for AI. You know, whatever rocks your boat. But all of them lack one thing, and that's privacy. Probably a big reason why you're here. I have come to dislike the word privacy because it has, for some reason, some bad connotation in the space. However, you know, when we're trying to define it technically, then we still have to use the right term. And the right term is privacy. And when we talk about privacy, we usually split it into two pieces. Anonymity, which is more like the metadata. You know, when you're sending like a Bitcoin transaction, an Ethereum transaction, then maybe you want to hide who the sender and the receiver are. And then there's the actual data. And in something as simple as a transaction, that is like the amount. Okay, it's not that interesting, at least in my opinion. But when you go into smart contracts, when you go into like any kinds of computation, right? Like maybe you're using like ChatGPT, and imagine there's actually a decentralized viable ChatGPT, then you know you want to actually hide your query to that instance. So that's where things become interesting, because now you really have to hide any kind of data from the servers, from the network, from anyone who's observing. And you know, this is, unsurprisingly, has become something that many people are working on. So, you know, for those who don't know, I founded Secret Network before, who's working on that problem. I'm working on Fhenix now, who's working on that problem. Many people have tried to work on it both in industry and academia. And it's not an easy problem. And you know, when we kind of define the problem, maybe a bit graphically, then it's really as simple as you have users, they have a blockchain, they have a network, and they want to execute some computations over their private inputs. So when you see a log, that means that it's encrypted or it's privatized somehow. And also in contracts, we have this persisted input called the state. And then really the magic is like that we need to use some magic technology like FHE or MPC or you name it to actually run computations without actually seeing what the data is. Like that's actually the hard part. And then we get the output and the results. They can be encrypted, they can be public. So this might be a bit too high level, so maybe let's take one concrete example. So before I get here, how many people here have actually written or understand how a smart contract looks like? Okay, so this should be very, very easy for you. Imagine you have like a sealed bid auction contract, right? A very simple one, sealed bid auctions, they have many use cases. Not gonna get into them. I just wanna prove a point. So let's say you have Alice and she has a private bid, right? She sends that bid, there's a bid function, but the amount is actually encrypted. And then Bob does the same thing. And then Charlie, David, everyone else does the same thing. Eventually you have a lot of like encrypted bids stored in the state. And then Alice or anyone else just comes in and says, okay, let's execute let's actually execute the interesting logic, which is let's find out who the highest bidder is. And then the magic happens, and the only thing that's revealed is who the highest bidder was and how much they bid. Now, this is obviously where the magic happens, and to make the problem even more interesting, like what we care about is that the private inputs that are not the winner are never revealed. So let's say Alice here who bid 5, like her input should never ever be revealed to anyone. So, oh, interesting. That's the longer versions of the slides, so I'm gonna skip some for time, but all right. So how do you actually do it? How do you actually do private computation in a blockchain context? Well, there are 4 main technologies to do this. There's TEs. How many people know TEs here? Okay, good. So like I don't need to explain. Obviously they're great, they're fast, but they have some problems. There's ZK, which I'm kind of skipping for a second. There's ZK, which is actually the odd one out. It doesn't actually fit the framework. Like, for example, if you're trying to use like ZK to do like a sealed bid auction contract, well, it turns out that you can't actually do it. Because with ZK, you can only do it like one user at a time. Maybe they can prove something over their data, but you can't actually combine data. You also can do things like a private ChatGPT or things like that. Like those are really impossible with ZKP, but they are good for some problems. So when you're trying to stick to like pure cryptography, you really have 2 solutions. One of them is MPC. How many people are familiar with MPC? Okay, how many people actually know how MPC works though? Okay, still quite a lot, nice. So you have MPC and then you have FHE. And in my personal opinion, like when we're thinking like 5 years ahead within blockchains, it's gonna come down to kind of like these 2 variants. And kind of like the trade-off between MPC and FHE is that MPC kind of like optimizes, it has very fast compute because of the way it works. FHE has like slow compute, but it really, really suffers when it comes to latency and communication. And FHE is the opposite. Like compute is more expensive, kind of like ZK, even more, but communication is like minimal. And at least like in our opinion, and at least in my opinion, so those who don't know me, like I worked on MPC most of my life, or like the last decade, and I still think that like the better choice for blockchain is FHE, because I think it's much easier to optimize for computation than it is for communication. Not gonna go into details about FHE, but it's really, the idea is as simple as it gets. The details are the difficult ones. Like you have input, and whether you run the computations over the plain text, or whether you first encrypt it and then run it over the encrypted data and then decrypt, it's like the same thing. Like you can go through the square from all directions and you get to the same point. Really what it encapsulates is the ability to compute over encrypted data. And again, the most important part to remember is that communication is very, very, very succinct. It's very cheap, the only thing clients in the system, the only thing they have to do is they encrypt their inputs, they send it to the blockchain or to the servers or whatever, and that's it. Computation is heavy duty, but that's something that can be improved over time. So yeah, I'm gonna go very quickly over this, just kind of as a sidebar on a high level, but I don't want to focus about it too much. One thing that's kind of clunky with FHE, the way we know how to do it today, because it relies on the learning with errors assumption, is that encryptions are noisy. And that basically means that when you encrypt data, you have some noise. The noise is really the bar that you see here. It's like in orange. And when, let's say, you add two ciphertexts together, then the noise increases a little bit. When you multiply ciphertexts together, then the noise increases by quite a lot. And this is not a problem in this case, but what if we already had ciphertexts that already had more noise into them to begin with? So then you actually might overflow, and you may actually get like more noise than you're allowed. And then like the result here, the result of the multiplication is completely, like you can't decrypt it. Like you would never, like you can't actually recover the plain text from that. So one thing that FHE has, and like you don't see that in MPC or like other places, is this like special bootstrap gate. And really a bootstrap gate, all it does is it takes a ciphertext, you apply homomorphically that gate, and then it basically gives you a new ciphertext of the same value, but it basically eliminated most of the noise, and you kind of like get to start over. The problem was that, that Bootstrap is pretty complicated, especially in some specific FHE schemes. So TFHE, which we mostly use today, and that is also based on Zama's libraries, and most people in blockchain are working with TFHE. In TFHE, actually, Bootstrap is quite good. Like, you can actually do it like all the time. That's not actually a bottleneck. But you do pay, like, there's no free lunch. You pay for it in other places. Then there are some operations, like arithmetic operations, some kinds of circuits that you can't really do that well and that fast. But it's very, very easy to bootstrap. Another technique that people usually use and that we are currently exploring at Fhenix is that of like leveled FHE. So leveled FHE is really just a fancy name of saying, let's just like we need to know what the computation and the data is a priori. We need to kind of bound it so like the computation is not too big. And then we can kind of set the parameters of the entire system such that we never actually get, by the output, we never fill the bar all the way such that we need to bootstrap or we can't decrypt. I can't stress enough. I know if there's like maybe 2 or 3 important takeaway messages here, but I can't stress enough that there's no silver bullet. Like, when you're trying to choose what to use or what to do, eventually there are places where you would want to use like maybe TFHE and Bootstrap, and maybe you want to use something else and Bootstrap, and maybe you want to use a level scheme. Like, it's really, really, I don't think there's like one solution. And like, if I may make some prediction, I think that over time, we will get to the situation where we really want to focus on scheme switching, like throughout computations, and actually mixing and matching between different techniques. Okay, so end of sidebar, end of like going a little bit into FHE, although this is very, very high level. At Fhenix, what we did is kind of like we took a different approach to scalability. So, one way to scale FHE is to improve the algorithm. Another way is to optimize the parameters per computation and optimize the circuit. But a third approach is basically to look at FHE as a black box and then think about how it manifests in the blockchain ecosystem. And when you think about blockchains in general, and this should be known to all of you, like you pay a lot, right? Like whenever you have a layer 1 blockchain, then everyone has to replicate a computation because they need to reach consensus. Plus the time for consensus is like non-negligible, right? Like you have to wait for like a majority of nodes to reach agreement. That takes time. with FHE ciphertexts are big, so all of that kind of blows up and it becomes pretty unscalable. So instead, at Fhenix, what we did is just we took a node from L2 rollups, and we said, okay, let's actually separate execution from verification. So the blockchain up on top does the verification. That's as usual, how it operates like with L2s. And then the execution can just happen by even a single beefy, big server with GPUs or ASICs or whatever, the industry gives us, kind of like off-chain. And then you don't actually have to replicate the computation, and you don't have to reach consensus in real time. And that's big. And that's exactly what we've built. So we built a rollup that is focused on FHE. And other than the fact that pretty much all contracts run FHE code, there are two main problems when you're trying to kind of take plain text rollups into the encrypted realm. One of them is decryption, and the other is how do you actually prove the computation. And so, when it comes to decryption, this magical FHE thing is nice, like you can compute over encrypted data, but sometimes you have to decrypt. Like, remember the auction contract that we had? So in the auction contract, like, everything happened over encrypted data, but at the end, like, the contract needed everyone to know who won. And that's a value that needs to get decrypted, so how do you do that? Who holds the key? We don't want one person to hold the key for obvious reasons, so what you do is you do an MPC protocol, you split the key across the nodes in the network. There's a lot of subtleties here that I'm not going to get here, and I'm, again, happy to geek out later. But I will say that on the positive side, this gives us like MPC assumptions in the system that are kind of similar to already the assumptions that we have in blockchain systems. The one drawback, which I do think is important, is that usually faults, like, in a blockchain, like, you assume that the majority of the mining power or validating power, staking power is honest. But if they're not honest, then you can slash them, then you can do stuff. Those are like observable faults. The problem here is that these faults are usually not observable. I actually think we as an industry need to put a lot of work into how can we improve this, but that's, I'm going to leave it at that. But that is something to keep in mind. The other part is, okay, how do we actually prove that FHE computations are correct? So you can use ZK proofs, way too slow. The Zama team has actually made some amazing progress there. But even like proving a single bootstrap gate, not an entire computation, a single bootstrap gate still takes like 30 minutes. So it's like not practical today, maybe in the future. The other aspect is fraud proofs. And for those who don't know fraud proofs, let's say there's just one transaction. So a fraud proof is basically a three-party game. You have the sequencer, which is the prover. They basically ran a computation, and then they just put like the transaction and the result on the blockchain or some data availability layer. And then anyone for like some period of time can come in and basically say, you know what, I think that the prover actually cheated, and raise a dispute. And then there's this bisection game, which is really just about pinpointing like the single opcode where there's a disagreement between the prover and the disputer. And then the blockchain itself can actually just run that one opcode specifically, and that is relatively efficient, and then they can decide who cheated. The problem is that Solidity is not compatible with FHE. And we don't want to make, like, we're not going to go to Ethereum validators and convince the L1 to actually change like the code that they're running. So what we do is we work with Arbitrum. Luckily, Arbitrum is like a fantastic stack when it comes to like WebAssembly-based fraud proofs. So they built like a WebAssembly interpreter that runs in a contract, and we're using that. And then essentially, it doesn't matter that our code is Rust. And then it compiles down to WebAssembly, and we can still play the fraud-proof game on-chain even so. I will say that it's inefficient, but luckily this isn't something that needs to happen very frequently, if ever. A couple of last notes. The thing I like about FHE contracts, and that's really, really an advantage compared to like, if you ever try to use like ZK for privacy, stuff like that, is that FHE contracts are simple. Right? It's like take Solidity, switch the types, use like a special library, and that's it, right? For like operators, for encryption, for decryption, and that's it. Like you don't have to really learn anything else. If you wanna do like more optimizations, then you do, but on a high level, you don't have to. And just to be clear, like this is not in theory. We built this, we implemented it. It works in practice. There's still a long way to go when it comes to efficiency, but like you can run like real contracts in hundreds of milliseconds, so maybe a few seconds, and we do think we'll be able to like 3 to 10x this by mainnet. And this was run with like pretty simple hardware, like not really that expensive hardware. So one last note, I'm running out of time, but I will just mention that we kind of realized over time that a rollup is really a coprocessor in disguise. A coprocessor is just the ability to, you're working on some chain, and then you want to outsource some computation to some coprocessor. So an FHE coprocessor allows you to basically use Fhenix, not in its own L2, but like on the Ethereum L1, on Arbitrum, on Optimism, wherever you want. And yeah, if you're a developer, you should really go there or talk to Kyle or talk to me or talk to Tom here and really get an idea of what you can build there. There's a lot of stuff you can do. And I'm out of time, so thank you very much.